Red Hen, and I am going to talk about the small intestine today. So, here we go. Small intestine is a convoluted tube extending all the way from the pyloric sphincter, right here, to the ileocecal valve where it joins the large intestine, right here. It is the longest part of the alimentary canal and is about 20 feet long, but only 2.5 to 4 centimeters thick. Now, why is this? Because in this part of the alimentary canal, it is making sure that there is maximum digestion and maximum absorption of the digested food. Nothing is wasted. It has 3 parts: duodenum, jejunum, and ileum. The duodenum is only 25 centimeters long and is the shortest intestinal subdivision. The pancreatic duct opens with a bile duct to drain into this part, the duodenum. The jejunum, the next one, is about 8 feet long, and the ileum is about 12 feet long. Both ileum and jejunum hang in sausage-like coils in the central and the lower part of the abdomen. The small intestine has several functions. First, it receives chyme from the stomach and secretions from the liver, gallbladder, and pancreas. Remember, gallbladder is just a storage unit, so it will be more correct to say secretions from the liver and pancreas. It completes digestion of nutrients in the chyme. It absorbs, main function, absorbs digested nutrients. It transfers nutrients to the blood or lymph for distribution to the rest of the body. And last but not the least, it transports the remnants of digestion, which is now almost waste, to the large intestine. All right. Like I said, let's look at the walls of the small intestine. The small intestine is adapted for absorbing nutrients. Its long length and structural modifications allow for increased surface area of absorption. If you remember what I said, this is the place where maximum absorption has to take place. So number one, there are circular folds of small intestine that are deep, and these deep permanent folds of the mucosa and submucosa are about 1 centimeter tall and is called plicae circularis. This will force the food to pass through in spiral patterns through the lumen, and therefore because it's passing spirally, it's going to slow it down. Why do you want slow passage? Because you want maximum digestion and absorption. Then finger-like projections called intestinal villi of the mucosa, which are about 1 millimeter tall. And this villi, not to be outdone, has microvilli, which are absorptive cells of the mucosa, have long microvilli that give a fuzzy appearance called the brush border. Let's look at the histology of the villi. Well, the villi, if you see the villi, the epithelial cells of the villi are chiefly absorptive columnar cells, as you can see from here, and made up of simple columnar epithelial cells. The cells have very tight junctions and also have microvilli. We have already talked about that. There is a connective tissue in the core. So right in the core, inside is connective tissue. And this core contains, what does it contain? Blood capillary network, a very rich supply, nerve fibers, as well as a blindly ending tube, which is called a lacteal, which is nothing but a special lymphatic capillary. Blood capillaries and lacteal, what do? They transport the nutrients which are absorbed by the columnar cells of the columnar epithelial cells. There are also goblet cells. Goblet cells always have one function, and that is mucus secretion. So the food is as the chyme is passing through, more and more mucus is added. There are intestinal glands. In between the villi are crypts, and these crypts or pits, and these pits, as you can see right here is a pit, that lead into glands, and these glands secrete a very watery fluid. The fluid contains some mucus and serves primarily as a carrier fluid for absorbing nutrients from the chyme. There are also the enteroendocrine cells. So not exactly glands as such, but you have enteroendocrine cells, and these are going to be secreting the typical enteric hormones such as secretin, and the other one is cholecystokinin. Secretin will increase, we have talked about secretin before, secretin will increase the bicarbonate secretion from the pancreas. Cholecystokinin will inhibit stomach motility as well as stomach secretion. There are also special cells called the Paneth cells, and these Paneth cells, these secrete the lysozyme. Lysozyme is an antibacterial secretion which will break down the bacterial cell wall. However, look at the beauty of Mother Nature. Lysozyme will determine which are those bacteria that can colonize the intestinal lumen. So not all bacteria can colonize, only some bacteria can colonize which are not damaged, destroyed by the lysozyme. The mucosa also contains individual follicles and aggregated lymphoid nodules. The nodules are called pear patches, and these pear patches are located primarily in the lamina propria, and these pear patches do not allow the entry of bacteria in the large intestine. There are special cells, T cells, and these are called the epithelial lymphocytes, or the intraepithelial lymphocytes, IEL. Okay, these are important defense components. So all right, now let's look at the next slide, and that is about the digestive enzymes. The intestinal juice, first of all, is primarily watery and very alkaline. Okay, it's about 7.4 to 7.8. What are the digestive enzymes? Well, the fluid secreted by the intestinal glands, I would not say does not, but is very poor. It contains poor amount of digestive enzymes. Okay, the fluid mainly helps in the absorption of nutrients in the villi. So here, in the large intestine, the final phase of digestion takes place, so that now there's complete breaking down of food molecules just prior to the absorption of the cells. The digestive enzymes are embedded in the membrane of the microvilli, so they are right here. And as the food is being absorbed, it is going to complete its digestion. So complete breakdown of molecules such as the enzymes are peptidases, which will break down peptides to amino acids. If you remember, the protein digestion had started in the stomach. Then there's sucrase, maltase, and lactase, which will split disaccharides such as, this is wrong, this should be sucrose, fructose and galactose into monosaccharides such as glucose. Final phase is like intestinal lipase. Fats are broken down into fatty acid and glycerol. If you remember, fat digestion had started a little bit in the stomach, but cannot take place well because the fat is not emulsified. All right. So what is digestion? Digestion is a breakdown of molecules into subunits. carbohydrates is nothing but a chain of monosaccharides, and so here what happens is the digestion of carbohydrate you end up with monosaccharides. Proteins are nothing but a chain of amino acids, about 20 amino acids. So proteins are finally broken down into amino acids. Lipids are broken down into fatty acid and glycerol. And nucleic acids are broken down into nucleotides. And what are nucleotides? Nucleotides, these subunits, my pen is acting up, excuse me, are made up of one nitrogenous base, which could be ATGC. It is one pentose sugar and one phosphate. This is one nucleotide. Nucleic acids are made up of many nucleotides. Okay? So why digestion? Well, when we are breaking down into subunits, into the monomers, when we are breaking down polymers into monomers, these monomers either are used as building blocks to make new biological macromolecules, or they can be used as energy sources. Alright, so let's look at individual digestion. Let's start with carbohydrate digestion. Carbohydrate digestion starts in the saliva with the salivary amylase, if you remember. Okay, so here what happens is in the mouth, the polysaccharide is broken down into oligosaccharide, and then what happens is the final phase of that digestion is completed by the pancreatic enzyme, which continue digestion to the disaccharides. Finally, if any of the disaccharides have escaped digestion in the small intestine, enzymes in the microvilli will break down disaccharides into the final monosaccharides. So now the monosaccharides are taken up into the columnar epithelial cells. This is by active or passive transport. Please look up active and passive transport across the cell membrane. So once they're released from these epithelial cells, they enter the blood capillary and transported to the places that they are required. Now let's look at the protein digestion. Protein digestion, if you remember what proteins are, which is it's just a polymer made up of many amino acids. Protein digestion starts with pepsin in the stomach and completed, and then goes on into completed by the pancreatic enzymes, which help digest proteins into peptides, or what happens is small chains, which we could call oligopeptides. And finally, what happens is these short chains of amino acids, which you could call oligopeptides, is completed by the peptidases in the microvilli, which will break the peptides into amino acids. So once again, complex protein, here's my protein, is being broken down into shorter chains, which are oligopeptides, which are broken down into amino acids finally, and then it is again transported across the membrane by active and passive transport, and then transported finally by the blood, very similar to the monosaccharides. Okay, let's look at fats. Fats starts with the lipases. If you remember, the lipases first attack the fats in the stomach. So here what happens is very little digestion takes place because fat has to be emulsified. What is emulsified? Big chunk of fat is broken down into small chunks. If you remember, fat is not water soluble, and therefore what happens is when you break it into smaller pieces, now the enzymes can act on its surface and break it down into fatty acid and glycerol. But the different scenario exists in the duodenum because right here in the duodenum you're getting bile salts which will create the emulsification. So now lipases from the pancreas can break it down into fatty acid and glycerol. Any fat that escapes the pancreatic juice is finally broken down by the lipases in the microvilli. Now fatty acids, now remember, they are not water soluble, right? So what happens? How are they absorbed? Well, the they diffuse through the cell membrane of the simple columnar epithelial cells. And they can do this. How? They can do this because they are, remember, hydrophobic. Okay, so now once inside these cells, fatty acids are used as building blocks to produce new fat molecules, and this occurs in the endoplasmic reticulum. Fats form clusters, and they get this, so this is a fat, they get clusters and they get encased in protein, and this is called a lipoprotein. Okay, this is all taking place in the epithelial cell right here. Okay, then what happens is you can also find chylomicrons. What are chylomicrons? Chylomicrons are just large lipoproteins. Okay, and these chylomicrons are transported out of the simple columnar epithelial cells of the villi, and they will enter the lacteal. If you remember, lacteals are just blindly ending lymph capillaries, and they will enter into larger lymph vessels called cisterna chyli, and these empty into the thoracic duct, which empties into the left subclavian vein. So in that way, what happens is fat is digested, absorbed, and returned to the blood supply. Okay. Because fats are insoluble in water, they thus cannot circulate freely in the blood. So they are transported in lipid protein complexes called lipoproteins. We know that, right? Now there are three types of lipoproteins. Chylomicron comes in a total different category, okay, and they have a lowest density. We talked about that. Chylomicrons are nothing but few lipoproteins. So if this is a lipoprotein, so here you will have just a bigger chylomicron. But so they come in different category. But the others that are seen, the bigger categories, will be the VLDL, very low density lipoprotein, LDL, this is the low density lipoprotein, and the high density lipoprotein. Let's look at each one of them. The VLDLs are produced in the liver, and they transport triglycerides generated from excess carbohydrates in the diet from the liver. Chiefly from the liver, they go to the adipose cells. Okay, so these are the ones that will go to the adipose cells and help to increase fat of your body. Right. So these also contain a little bit of cholesterol. So once in the tissue, this VLDL is converted into LDL, which we are going to talk about next. The LDLs have a higher cholesterol level than the VLDLs, and its primary function is to deliver cholesterol to other tissues. Why is this necessary? This is necessary because all cells need cholesterol molecules for what? For their plasma membrane, number one. Number two, the LDLs is taken up, and LDL is broken down in these cells, to whichever cell, is broken down into cholesterol. And remember, cholesterol is also needed for the making up of the steroid hormones. Okay. Now let's look at the HDLs, the high density lipoproteins, which are also produced in the liver. It has a very high content of phospholipids. But what its function is, it removes excess cholesterol. So it removes excess cholesterol from the tissues and transports it to the liver. So this is what you need in your body. It's taking excess cholesterol and is removing it into the liver, and liver removes it, secretes it in the feces. All right. So HDL also, like LDLs, provides steroid-producing organs such as ovaries and adrenal with raw material. Okay. Let's look at the electrolytes. The cell lining the intestinal villi also absorb water and electrolytes. Very important. Sodium, potassium, chloride, nitrate, sulfate. These are absorbed easily. Okay. Calcium, magnesium, sulfate are absorbed very, very poorly. And electrolytes, they are absorbed by active transport, and so therefore they will require a carrier protein, or they will require a channel protein, which If you cannot remember what they are, please go ahead and look up your 201 notes. These are your membrane proteins. Now the water is absorbed mostly by osmosis. Please make sure you understand what osmosis is. At first, the contents of the small intestine, it is hypertonic. But as water is absorbed, therefore what happens, as nutrients is absorbed, then what happens is the contents of the small intestine become hypotonic. And this allows water to flow from the lumen of the small intestine to the inside of cells lining the villi. Okay? Small intestinal movements. We see two types of movements here, and the first one is segmentation and the second one is peristalsis. Now segmentation will allow the food to be almost massaged, or better said, it moves forwards and backwards, and therefore what happens is sloshing the chyme back and forth so that proper mixing of the food takes place. And it's mixed with the digestive enzymes, proper digestion takes place, and of course proper absorption takes place. As with the stomach, the intrinsic pacemaker in the circular smooth muscle layer initiates these movements. Then there is peristalsis, which propels the contents through the small intestine. Now it's a slow process, and it generally lasts about 3 to 10 hours from one end to another end. And who stimulates this movement? As usual, parasympathetic stimulates the movement and therefore digestion. Sympathetic, if you remember, will inhibit movement and therefore the digestion. What is diarrhea? Well, diarrhea occurs when small intestine walls become overly distended or irritated. And it could happen because there is too frequent excess amount of parasympathetic impulses reaching the small intestinal walls, and as a result of which there's a peristaltic rush through the small intestine. Okay? And as a result, because of diarrhea, water, nutrients, electrolytes are not absorbed well. Of course, there's going to be imbalances. In this connection, the ileocecal sphincter, so the small intestine opens up into the large intestine, if you remember. The large intestine, oops, my small intestine should be, I'll just redraw it. I'll redraw it. So the small intestine, which is much more thinner, opens into the large intestine through this valve, which is the ileocecal sphincter. This usually remains closed and connects the ileum to the cecum. When does it open? It opens under two influences. Neural, that is because of a nerve stimulation. Two, hormonal. So if there is a gastroileal reflex, this, triggered by the stomach activity, increases the force of segmentation and therefore force it to open. Or gastrin, which is released again by the stomach, which increases the motility of the ileum and relaxes the ileocecal sphincter. So I think this is the last slide, and with this I thank you for listening to me, and we will talk some more in class. Goodbye.